for potassium, if the membrane potential is -90, that is when we have hit electrochemical equilibrium with potassium. So if the membrane is at -90 millivolts, that means there's an equal amount of potassium leaving the cell, and there's an equal amount of potassium ions coming back into the cell because of the electrical gradient. And it's only when we see the membrane potential at -90 degrees do we see that balance. You follow me so far? Now, you can play the same game with every ion, right? Instead of making a leak for potassium, you can make a leak for sodium, or you can make a leak for calcium, or even chloride, and you could play the same game, and it would come up to different membrane equilibrium potentials. And they will vary dependent on various things. And that's what this equation above represents. This is called a Nernst equation. I don't need you to memorize this equation. I want you to know what goes into the equation. What goes into the equation is the chemical gradient, right? We're looking at how many ions are on the outside versus how many ions are on this side. And what else goes into it is the charge. That's what the Z stands for. And this value of 61 is comprised of a couple other things, which I'll talk about in the next slide. But yeah, based off the chemical differences and the charge, you can determine what this equilibrium voltage would be like. And so that's what we have here in this table here. Given these differences and the charge that you see here, you can calculate these if you just follow the Nernst equation. And I want you to notice a couple things, right? It kind of makes sense, right? Potassium is a positive charge. And so it makes sense that the equilibrium point is going to be at a negative voltage. Because if it's a positive voltage, this wouldn't happen, right? There would not be an electrical gradient coming back into the cell. If you look at calcium, it has a negative charge, so there's going to be flipped. So there's going to be a positive equilibrium potential. So this doesn't make 100% right away. Review it a couple times. Think about it. Take some time. Still not making sense? Come find me. We'll talk about it more. But the thing is, in a real cell, all these ions are in play, right? There's just not one leak. There's not like a leak for one ion at a time. All these ions are in play, and all these ions are making a charge difference, right? And so the Nernst equation is not going to be good enough to understand what the membrane potential is going to be like, right? The membrane potential is not -90, right? Millivolts. I told you it's -70. None of these are -70, right? So how did we get the -70? Well, you get it from this equation called the Goldman-Hodgkin-Katz. Believe it or not, those are three people that made up this equation. And that's what the equation looks like. Now this equation looks even scarier. I'll say this again. You don't need to know this equation, but you need to know what it's about. So here, you can see a lot of similarities. See, this is the ion out over the ion in. Well, that's what this is. This is the potassium on the outside versus inside. This is the sodium on the outside versus inside. And this is the chloride versus what's on the inside versus outside. The reason why it's flipped is because chloride is negative. So it's flipped. Now, these random factors is where we get our 61. If you have to know what that is, T is temperature, and R and F are, well, R is the ideal gas law constant, and F is a Faraday's constant. You don't need to know that. Just need to know those constants, and one of them belongs to temperature. And then Z is our charge. And the special thing about this is this p-value, and each ion has this p-value, and P stands for permeability. So what goes in the equation is how permeable these ions are to the cell membrane. And it varies. For example, potassium is 40 times more permeable than sodium is. And so that makes it different, right? If sodium can leave the cell much more easily if potassium can leave the cell membrane much more easily than sodium, that's going to have a bigger effect on what the equilibrium potential is going to be. So, if you take all of this information, put it in there, and you collect information about permeability, all this will get you your negative 70 millivolts. That's how we arrive at negative 70 millivolts. And so that's kind of what goes into it. What do you think controls permeability? Concentration is part of it, yeah. What else? If it was just a phospholipid bilayer, would there be any permeability? No, ions don't normally go through a phospholipid bilayer, remember?
There's channels.
There are going to be channels. There are going to be transporters that help with permeability. So some of these channels are called leak channels, meaning they're kind of like these open gate channels that just kind of let their selected ion through. And the permeability is going to depend on how many of these are open, how many are there in total are there in the cell membrane. All these will give to the total permeability of a certain ion. And just like because these are transporters, these are proteins, we can modify them, we can change them. So sometimes we can make, let's say, sodium ion channels we can make sodium more permeable if we open up more sodium channels, or if we can reduce the permeability of potassium by closing more of these potassium channels. And so by doing that, you can change the voltage, right? If you can change the permeability, you can change these guys, you're going to change this. You're going to change that negative 70, and that's what you're seeing on this graph. Here we have our membrane potential. It normally sits at negative 70. But if you change the permeability, you can increase the permeability. When we increase the permeability, we say we're depolarizing the membrane, because we're bringing this value closer to 0. When you have a voltage difference of 0, you have a neutral polarity. That means you're not really polar, you're kind of non-polar. But if you're further away from 0, that means you're polar. So if you're bringing the voltage closer to 0, you're depolarizing the membrane. And if you bring the membrane potential further away from 0, you're hyperpolarizing it. You're making the cell even more polarized than it normally was. And these can act, these differences in membrane potential act as signals. Cells can react to different changes in membrane potential and do various things, and that's the crux of the nervous system. The membrane potential changed, do something. Did it become hyperpolarized? Maybe it do something, maybe it's to inhibit something. Nervous system can act as an excitatory or an inhibitory response. So oftentimes hyperpolarization is inhibitory, while depolarization is oftentimes excitatory. That's one way of looking at it.
So hyperpolarization also means that it becomes less permeable?
No. So we're changing, we'll address this soon, we're changing the permeability to either make it depolarized or hyperpolarized. And then we have all these different levers to do this with, right? If we, for example, if we, and we'll talk about this in a couple of slides, if we reduce the permeability of potassium, that means we're retaining more potassium in the cell. There's more positive charge in the cell. That means we have a lower membrane potential because we're keeping more positive charge inside. That's depolarizing, and we're reducing the permeability in that sense. Or we can increase the permeability of chloride. That brings in more negative charge into the cell. That makes the membrane potential more negative. That's hyperpolarization. Or we can turn off chloride ion channels completely, and that depolarizes the cell. There's a lot of different levers, and they move in different ways. You guys should all be comfortable in understanding how the membrane potential changes by changing the permeabilities up and down. That's an easy exercise to do. Pick an ion, pick how the permeability changes, and be able to determine if you're going to depolarize or hyperpolarize your cell. And we'll go over a couple examples soon. Moving on. So here are the various ion channels. These are the guys we are modifying to change permeability. We have our sodium channels, calcium channels, chloride channels, sodium, potassium, chloride, and calcium channels. And we also occasionally have these monovalent cation channels, meaning they only are going to take on cations that are unitary. So basically not calcium. That means they're taking in calcium and chloride. And so if this was on the inside of the cell and this was on the outside of the cell, is potassium high or low on the outside of the cell? Oh, sorry, let me rephrase that. Is calcium high on the inside of or the outside of the cell?
Inside.
So there's a lot of calcium here, and there's a lot of today's not the day for saying words. Potassium is high on the inside, and sodium is high on the outside. And so you'd be like, well, what's the point of this, right? If you just open this up, this would go here, this would go out. There'd be no net change. That's silly. But it turns out there is a higher gradient of sodium than there's a gradient of potassium. So much more sodium is going to be flowing out as there are going to be potassium. There's going to be much more sodium flowing into the cell than there will be potassium